Okay, so in some treatments, what this remark says, in some treatments of natural numbers, 0 is not considered. That is, 0 is not considered to be a natural number. And for them, the natural numbers start with 1. So, the natural numbers are the numbers these numbers are considered to be the natural numbers. Now we have decided to include 0. This is just a matter of notational convenience. Whether you consider 0 to be a natural number or not, the mathematics does not change. So for us 0 is a natural number, for some people they are not, it's not. So for us the set of natural numbers looks like this. Okay. Granted, of course, this is informal, right? Because as yet we don't know what these symbols mean, but we will soon define them. Now the thing is that for us these are the natural numbers, for some people these are the natural numbers. They don't consider 0 to be a natural number. For them, if they include 0 in the set of natural numbers, the corresponding set is said to be the set of whole numbers. For us, this set will be called the set of positive integers. Eventually, when we introduce integers, they will become the positive integers. So that's just a notational remark. Now we will define these symbols 1, 2, 3, etc. Okay, I don't have to wrap this one. Now we can look at these symbols. We want these to be the natural numbers. But the symbol is, the notation is unmanageable. You can see that even to write the fifth term in this sequence, we have to use this incrementation operation 4 times, because that's what we get. We get the fifth element by incrementing 0 4 times. Right, so that's why we need to find a neater or more compact notation. For that, we have this next definition. Definition 213. So what this definition says is very easy. It defines this, it gives names to these symbols with which we are already familiar. It defines 1 to be this, the element next to 0. Similarly, 2 is the element next to 1. 3 is the element next to 2. Or 3 is the increment of 2, etc. It goes like this. There is one more terminology that we can use, the increment n plus plus of a natural number n is also called its successor. successor as opposed to predecessor. Successor is the next one, predecessor is the previous one. So for example, we can say that 0 is the predecessor of 1. So this allows us to write these things in a more compact way. This is 1, this is 2, this is 3, in the usual way that we already know. Now this is where we use the decimal representation or decimal system in writing these symbols. We use the decimal system to that extent only. Nothing else, no other knowledge of the decimal system will be used. And note one more thing, that we continue to think of these entities just like that. 1 is the successor of 0, 2 is the successor of 1. Whether you write them using decimal or you write them using some, even you can use Roman numerals, nothing will change. So that's why the mathematics that we will develop is not dependent on the system in which the numbers are written. Okay. Right. Now we are ready to introduce the piano axioms. Now let us have a look at this list. It goes on and on. Okay. We want this list to have or to consist of the natural numbers. We want these objects to be natural numbers. So what are the assumptions we have to make? We have to make assumptions because as of now we are not given anything except we have a number 0 and we have an operation known as the incrementation operation, which produces something next to what is being incremented. So if we think of that, then immediately we get two assumptions regarding this whole thing. Two assumptions or axioms. Axioms are assumption. Well, axioms are some statements which are not proved. They are taken to be correct in the sense that they are easy to believe in. Okay, and they are very fundamental. We believe in them because they seem to be correct. They are not proved using something more elementary. You start from some axiom and then develop a logical system. So that's how things work. If you keep on asking why something is true, then you will go in the opposite direction. I mean, you have some object, you want to define it in terms of something more elementary. Then that something more elementary, that for that also you demand that to be defined in terms of something even more elementary. So if you keep on doing this, if you don't stop somewhere, you will go in the backwards direction. You will not progress anywhere. So at one stage, things become so elementary that they are somewhat self-evident. They are believed to be true. So from there, taking them as the basis of our theory, we have to then develop. So that sort of things are now going to be given here. So based on this discussion, the first axiom is this. Axiom 2, 1. 2 represents the fact that it's appearing in chapter 2. Okay, this does not follow the usual way in which we are numbering the items in this section or in the chapter. So axiom, and that's because there are only so many axioms. Apart from these axioms that we will discuss now, the piano axioms, there are some other axioms in axiomatic set theory that we will come across. So taking them together, we have the Jarmelo-Frankel set theory, where the assumptions are taken as the basis of our theory and everything else is proved in using these axioms. Anyway, so the first one is this: 0 is a natural number. Because we want 0 to be a natural number, so we make that axiom. Next part, we also want the other numbers to be natural numbers as well. So do we have to say 1 is a natural number, 2 is a natural number? Do we have to make that axiom? We will, but not like that. That's why we have this operation, this incrementation operation. We will make that axiom, or which looks like infinitely many axioms, using only 0 and this operation, because that's how the other numbers are being generated from 0, step by step. So the next axiom is this. The second one, axiom 2.2, for any natural number n, its successor n plus plus is also a natural number. So it seems that we have captured everything that we need. 0 has become a natural number, and whenever something is a natural number, then the next one, the successor, is also a natural number. These are the assumptions. Okay, so it seems that that's all. Using these two assumptions, we have defined the set of natural numbers. Okay, operation is a different thing altogether. In fact, in trying to understand how to define operations, we found out that there is an elementary operation known as incrementation. Eventually, this will be used in defining addition, multiplication, and exponentiation, but that will come later. First of all, we are defining what the elements are, or what the objects are in this system. So it seems that these two axioms are enough for everything, I mean for that job. But now the problems will start. Okay. And the problems start like this. Let me just keep the list and wrap the other things up. Okay, but before we go to the difficulties or the problems that these axioms encounter, let us just see a quick consequence of these two axioms. And the consequence is this: a very silly looking proposition. I have to keep the names and the order of the things the way they are in the text. Okay, so this is proposition 214. This is the fourth item. The previous one was definition 213, where we defined the symbols 1, 2, 3, etc. And the proposition says 4 is or 3 is a natural number. Yeah, 3 is a natural number. This is the proposition. Now it may seem somewhat silly. We already know 3 is a natural number, but keep in mind, we have decided to forget the prior knowledge of natural numbers. For us, 3 is just this object. Okay, we have to, if we are asked to show that 3 is a natural number, we have to show it. So here is the proof. And in proving this fact, we cannot use anything that we already know about natural numbers other than what we have seen here. I mean, not anything that we know before this discussion. So what we right now have is we have 0. We know that 0 is a natural number, and we know that whenever we take a natural number, its successor is also a natural number. These are the two things we have at our disposal, and using them only we have to prove that 3 is a natural number. So the proof goes like this. By Axiom 2.1, 0 is a natural number. So by Axiom 2.2, 1, which is the successor of 0, is also a natural number. Is also a natural number. See, first we have made use of Axiom 2.1 in deciding that 0 is a natural number. That is our first assumption. Now the second assumption lets us say that 1 is a natural number. Again, Axiom 2.2 implies 2, which is the successor of 1, is a natural number. Finally, one more application of Axiom 2.2 gives us the fact that 3, which is the successor of 2, is a natural number. And there the proof ends. It may seem like too much of something for nothing, but you have to keep in mind that this is how logical proofs go. Every statement we make in a proof should have some sort of justification. 0 is a natural number by the first axiom. So by the second axiom, its successor 1 is a natural number. Now we have 1 is a natural number. So again, by using the second axiom, 2 is a natural number, the successor of 1. Again, finally, by using once more the second axiom, we get that 3 is a natural number because it's the successor of 2, and 2 has been proven to be a natural number. So that's how we get the fact that 3 is a natural number. Okay. So this is one simple consequence of these two axioms. But now let's go to the problems that we will encounter in spite of having these two axioms. And the problems will seem somewhat surprising at first. And the problems will necessitate the formulation of more axioms. Okay, we will need more axioms. So let us take example. I don't know why I keep forgetting the number. Example. My short-term memory seems to be messed up. Example 215 is, consider the number system 0, 1, 2, 3. Okay, so I consider a number system in which there are 4 objects and 1 is of course 0, or since I am not defining, let me write it the other way. 0 plus plus is 1, fine. 1 plus plus is 2. 2 plus plus is 3. And 3 plus plus is 0. Okay. You will immediately tell me that what I have written is wrong, because according to definition 213, 3 plus plus is not 0 but 4. But who told you that 0 is not equal to 4? You see, you cannot use any prior knowledge. You have decided to set them aside and look at everything with an open mind, as if we don't know anything. We know 4 is not equal to 0, right? Because you see, if you look at definition 213, by that definition 3 plus plus is equal to 4. The symbol 4 is the successor of 3 plus plus. The successor of 3. But we have decided to make it equal to 0. The question is, in this number system, we have to check whether these two axioms are true or not. If they are true, we have a problem. Why? Because it says that these two axioms are not sufficient to capture our intuition of the natural numbers. We think that the natural numbers, not only they are progressing like this one by one, but they are going on indefinitely without any end. Here, however, things have cycled back to 0. We have started from 0, we have got to 1, whose successor is 2, whose successor is 3, but then the successor of 3 is taken to be 0. Now let's one by one see whether the axioms are true. 0 is a natural number. Being natural number means being in this system. Okay. I have proposed 2 axioms. Someone gave me this example and said, okay, so according to your axiom, this is the system of natural numbers. So 0 is a natural number, that is okay. The successor of every natural number is a natural number, or in this case, the successor of every object in this system is again an object in that system. Successor of 0 is 1, which is here, a natural number. Successor of 1 is 2, which is also here, it's a natural number. Successor of 2 is 3, which is also here, that is a natural number. Successor of 3 is 0, which is also here. So there is no problem. Both the axioms are true for this system. So clearly, something has gone wrong. Nothing has gone wrong with the axioms. But what this example shows is that these axioms are not enough for defining the natural numbers, or are not enough for defining the natural numbers that we have in our mind. Okay, we want to define something, but they don't fully capture the essence of the natural numbers. So we need additional axioms. And here comes the third axiom because of this problem. Axiom 2, 3. We don't want 0 to appear anywhere as the successor of some element. So that is our axiom. 0 is not the successor of any natural number. That is, n plus plus is not equal to 0 for every natural number n. So if we include this additional axiom, then this example is ruled out. Whoever gave me this as an example of a system of natural numbers, it's gone. Okay, so one difficulty is gone. So now we have a new axiom, and it now seems that everything is okay. Now life is again back to normal, right? Now okay, now because of our new axiom, we seem to have gotten rid of this difficulty. So let's just make another proposition and see what we have achieved. Proposition I have to put the number 216, because before this example 215 comes. So this proposition says 4 is not equal to 0. Okay, now with the additional axiom, we have to show that 4 is not equal to 0, because if here 4 is equal to 0, that is the difficulty, that is the problem with only these two axioms. We have to now show that 4 is not equal to 0 using these three axioms now we have. So let's look at the proof. If you, without any context, if you just look at this, we will be laughing at this, because we already know 4 is not equal to 0, but we don't know. Okay, now we will know 4 is not equal to 0. So in the hope of getting at some sort of contradiction, so suppose, what is happening? My writing is also going very bad. Suppose 4 is equal to 0. Then what is 4? By definition 2 and 3, 4 is the successor of 3. Okay, the 3 plus plus is equal to 0. But by proposition 214, I think, in proposition 214, 3 is a natural number. In that proposition, we have proved that 3 is a natural number. So 3 plus plus is equal to 0 contradicts axiom 2.3, because this axiom says that the successor of no natural number is equal to 0. But here 3 is a natural number whose successor is equal to 0. So this axiom is contradicted. So if we assume this axiom is true, then our supposition is wrong. So our supposition is wrong. That is 4 is not equal to 0. So now life is okay, except there is something else coming which will show that even these three axioms are also not enough. So let's take the next example. This is example 217. Again, someone is challenging me by producing another number system. Right, now in this number system, consider the number system. Suppose I decide to include one more thing. Consider the number system. Now I have to say what the incrementation operation does. The first few will be as usual. Successor of 0 is 1, successor of 1 is 2, successor of 2 is 3, successor of 3 is 4, but successor of 4 is 1. Okay. Now for this number system, let's see if the three axioms are satisfied or not. If some of them is not satisfied, then I will kick out that fellow who produced this example, because this challenge is weak. 0 is a natural number, that is the first axiom. Here it is there in the system. The successor of every natural number is a natural number, that is the second axiom. Successor of 0 is 1, that is here. Successor of 1 is 2, that is present. That of 2 is 3, that is present. That of 3 is 4, that is present. That of 4 is 1, which is also there. So second axiom is also true. Third axiom says that 0 is not the successor of any natural number. Here 0 is not the successor of any object here. You see, the right hand sides of these equations are the successors, which are 1, 2, 3 and 4. So that means in this system, instead of having things cycled back to 0, things have cycled back to 1. Okay. So this is another problem. So because all the three axioms so far we have introduced, they are satisfied by this system. And yet this system is also problematic, because in this system, after you see, for in this system 5 is equal to 1, because by definition 2, 1, 3, this is nothing but 5. In this system 5 is equal to 1, 6 is equal to 2, 7 is equal to 3. So that's not what we ordinarily see when we think of natural numbers. So in spite of having three axioms, they also fail to capture the full essence of natural numbers. Plus there are some additional problems also. Let us take one more number system. Consider another number system 0, 1, 2, 3, 4. Okay. So this is slightly different than the previous one. Here, in the beginning, everything is just like what we have in the previous example, number system, but the successor of 4 is again 4. So here, instead of things cycling back to some previous number, the number system has hit a ceiling. Here 5 is equal to 4, 6 is equal to 4, 7 is equal to 4. So from 4 onwards, all the other natural numbers are equal. Clearly this also will not work, because that's not what we want. Now there are many ways of tackling this sort of problem, or preventing this sort of examples from appearing. But one of the simplest is this axiom, another axiom we will need. This is axiom 2, 4. Because you see, here the problem is not 0 becoming the successor of something, or 1 becoming the successor of something. we can have some other sort of problems also. So what to do? Distinct natural numbers have distinct successors. That is, for natural